Okay, span, linear independence and basis, and row reduction. So in this video, we'll talk about span and linear combinations, a little bit about linear independence, row reduction, systems of equations of row reduction, and then finally basis and dimension. So span and linear combination, we've talked about span. So the span of a set of vectors, v1 through vn, is all vectors of the form some constant v1 plus up to some constant kn times vn, and each coefficient is allowed to vary from minus infinity to infinity. So this expression happens so much that we give it a special name. It's called a linear combination of a set of vectors. And so it's a vector of this form, where each ki has a particular value. So the difference between a span and a linear combination is you're picking specific values for the coefficients. The span is all possible linear combinations. So if v1 is 1, 2, and v2 is minus 4, 1, what are particular examples of this? So a linear combination would be, say, 4v1 plus v2. And just as to practice our multiplication, that's 4 times 1, 2, plus minus 4 times 1, 4, 8, plus minus 4, 1. And note that this 4 multiplies both the 1 and the 2, so we get 4, 8. And then when we're adding vectors, we add the components. And so that's the vector 0, 9. So that's a particular linear combination because we picked the numbers 4 and 1, and we multiply them by v1 and v2. Another one would be, say, v1 plus minus 2 times v2. Right, so technically it's adding a negative, but we can also just write that as minus 2v2. And again, that's 1, 2, minus 2 times minus 4, 1. So that's a 2. Plus, I'm just going to pull the whole minus 2 in there. So 8 minus 2 equals 9, 0. And so there's how we add those up. So these are two vectors that are in the span of these two vectors. So 0, 9 and 9, 0 are vectors that are in the span of these two because they're a linear combination of v1 and v2. So in example 2, we have these three vectors. We can get the same span with any two of these three vectors. So sometimes we have just too many vectors, right? We don't need all the vectors to get the same span. So geometrically, let's put this thing. Right, we can actually graph all of these things. So W1 is 1, 2. That's W1. W2 is minus 2 in the x direction and then 2 in the y direction. So that's W2. And then W3 is 1 unit in the x direction and 4 in the y direction. So you can see that W3, for example, you should be able to add W1, go along this line a little bit, and then add something parallel to W2 to get W3. So W3 is a linear combination of W2 and W1. So we could just use W1 and W2 to get the span of all three, because W3 is a linear combination of that. So W3 is in the span of W1 and W2. So you don't really need W3 in this vector. So arithmetically, what does it mean to be in the span? So the span is all possible combinations, linear combinations of W1, W2, W3. And so we want to know what kind of vectors are in of this form. What kind of vectors can I write of that form? And so we can expand this out. W1 is 1, 2. W2 is minus 2, 2. K3, W3 is 1, 4. And B is just some vector. We want to know what conditions have to be on B1 and B2 so that a vector is a linear combination of these. Now we can pull these together. We multiply in the K's. K3, we put little braces around everything. And then we can just add. When you add vectors, you add each component. Oh, that's a K1. It's 2K2 plus 4K3. So we just add the top row and we add the bottom row. We get B1, B2. And so this is two equations and two unknowns, and three unknowns, actually. And the second equation is 2K1 plus 2K2 plus 4K3 plus B2. Okay, so we want to solve this. I'll multiply the top. So these two become 2K1 minus 4K2 plus K plus 2K3 equals 2B1, because I multiply the top by 2. 2K1 plus 2K2 plus 4K3 equals B2. And now we'll subtract the top one from the bottom one. So, no, the bottom from the top. So 2K1 minus 2K1 is 0, minus 4K2 minus 2K2 is minus 6K2. 2K3 minus 4K3 is minus 2K3. And you get that. So what does this tell us? Well, we're down to one equation. Any choice of K3 will give me a choice of K2. And once I know K3 and K2, I can get K1. So we have infinitely many solutions. But that's because we have this K3 floating around. If we didn't have the K3, then we wouldn't have infinitely many solutions. What's the span? What could B1 and B2 be? Well, B1 and B2 can be anything. There's no restrictions on it because there's nothing weird going on over here. So the span is all of R2. And we already knew that from the picture. W2 and W1 pick out two directions in the plane. And so if I wanted to get to any point in the plane, I can go a certain direction along W1 and then go a certain direction, a certain distance along W1, and then a certain distance parallel to W2, and I'll end up at that point in the plane. So we can get that with any two of these three vectors can actually give us the same span. And the source of these infinities are in a sense, because we have too many vectors. And in fact, we can ask ourselves, what is the relationship between W1 and W2 and W3? So W3 is in the span of W1 and W2, means there must be a solution to this equation with alpha and beta not equal to 0. So this is alpha 1, 2 plus beta was minus 2, 2 equals W3, which is 1, 4. And if we do our usual conversion to equations, it would be alpha times 1 minus 2 beta equals 1. And then the bottom row is 2 times alpha plus 2 times beta equals 4. Now, if we add these together, what do we get? We get 3 alpha equals 5, which tells me that alpha is 5/3. And so this equation becomes, once we cancel out the 2's, alpha plus beta equals 2. Plugging in alpha and remembering that 2 is 6/3, that tells me that beta is equal to 1/3. So W3 is equal to 5/3 times W1 plus 1/3 times W2. And what does that mean? Well, whenever we're talking about linear combinations of W1, W2, and W3, we can replace this by 5/3 W1 plus 1/3 W2. And then we don't need to worry about having W3 at all. We can just describe the span of these three vectors as the span of W1 and W2. So in a sense, there's just too many vectors here. So throwing away these unneeded vectors, it brings us to the idea of linear independence. So a set of vectors is linearly independent if the only solution to a linear combination of these equal to 0 is each k1, k2, kn equal to 0. So these are linearly dependent because what do we have here? We have minus 5/3 W1 minus 1/3 W2 plus W3 equals 0. We have a linear combination of these three vectors where the coefficients are not 0, but they add up to 0. And that means that W3, you can solve this for one of the two vectors. W3 is actually a linear combination of the other two. So a set of vectors that is not linearly independent is called linearly dependent. So explain why the vectors in example 2 are linearly dependent. We just did that. Show that W1 and W2 are linearly independent. So that means we want to solve the criteria. The definition is that K1 W1 plus K2 W2 equals the 0 vector implies that K1 is 0, K2 is 0. When we started this, that was this sort of thing here on the right side. So K1 1, 2 plus K2. Now W2 was 2 minus 2, 2. I want this equal to 0. We rewrite this as a pair of equations. K1 minus 2K2 equals 0. 2K1 plus 2K2, 0. Add them up, we get 3K1 equals 0. That forces K1 equal to 0. And then that's K1. And then from this, well, from either one, that forces K2 equals 0. So the only possible solution is that K1 and K2 equals 0. Geometrically, what that means is W1 and W2 in the plane point in different directions. So they're linearly independent. So if you have a set of vectors that contains a zero vector, it's automatically linearly dependent. So everything we go in the future is sort of ignoring the zero vector. Well, if your set of vectors is k1 0 plus k2 v2 plus dot 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 plus kn vn equals to 0, you can make this say 7 times 0 plus 0 times v2 plus dot 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 plus 0 times vn equals 0. And then we have not all coefficients are 0 because we have a 7 here and it's equal to 0. So since this coefficient can be anything you want, that means if you have the 0 vector, you're linearly dependent. So we usually don't use the 0 vector. So what we see that is showing that a set of vectors in R2 or R3 is linearly independent. You can do a geometric argument, but if you're going to do higher dimensions, you need a algebraic approach, and this means handling a lot of different, a lot of vectors, a lot of equations, and we want to do it in a nice sort of mechanical way. So we'll do an example and then present some definitions, explicitly state the goal of row reduction, and do a few more examples. These are the rules of row reduction. Two rows can be switched, a row can be multiplied by a scalar, and two rows can be added and subtracted, and the new row that you get can replace one of the old rows. So how does this actually work? So these are linearly independent. So row reduction applies to equations of vectors. And as we saw, this turns into the equations k1 times 1 plus k2 times minus 2 plus k3 times 1 equals 0. And then k1 times 2 plus 2 times k2 plus 4 times k3 equals 0. So what we do is we set up something called an augmented matrix. And it looks like that. So this side sort of replaces the equal sign. This is the right-hand side. That's my 0, 0. This is the coefficients of K3, coefficients of K2, and the coefficients of K1. So K1 is coefficients 1 and 2, K2 is coefficients minus 2 and 2, K3 is coefficients 1 and 4. And this row represents equation 1, this row represents equation 2, and note that these columns are actually these vectors. Okay, so what can we do with this? We can, bar here, multiply row 1 by 2. And so that means take row 1, multiply by 2. That gives me 2 minus 4, 2, 0, 2, 2, 4, 0. Then we'll take row 2 and replace it with row 2 minus row 1. So that gives me 2 minus, well, we're leaving row 1 alone. So 2 minus 4, 2, and a 0. And then 2 minus 2 is 0. 2 minus minus 4 is 6. 4 minus 2 is 2, and 0 there. What I can do now is I can take row 1 and multiply it by 3/2. And that will give me 3 minus 6, 3, 0. And we're not doing anything to row 2, so we leave that like that. And then finally, now we can take row 1 and replace it by row 1 plus row 2. So 3 plus 0 is 3, minus 6 plus 6 is 0, 3 plus 2 is 5. We left this alone. And finally, the last step is to simplify everything. We'll take row 1 and we'll divide it by 1/3. And we'll take row 2 and we'll divide it by 6. So that gives me 1, 0, 5/3, 0, 0, 1, 1/3, 0. And so that's our row reduction. What's that done is it's taken these two equations and turn it into two new equations. Oh, this is supposed to be K's. Um, we'll just write over that. That should be a K1, and that should be a K3, and K2 plus 1/3 K3 equals 0. Great. And so there's our solution. Every choice of K3 gets me a choice of K1 and K2, and then we can plug those back in. There are infinitely many solutions, and so these things are linearly dependent because there are actually infinitely many solutions for that. Note also here a relationship among the running out of space. Relationship among the columns. We started with V1, V2, V3, W1, W2, W3. And these columns end up with K1. Well, the column, if we call this, we call this U1, U2. We call the columns U1, U2, U1, U2, and U3. What do we see? We see that U1, 5/3 times U1 plus 1/3 times U2 equals U3. And that relationship is exactly the same relationship that held among these three, right? That W3 is 5/3 of W1 plus 1/3 of W2. So that's one nice benefit of doing row reduction is it actually reveals relationships between your vectors. And that's why we want to actually get this kind of a situation here where we've got a 1 and a 0, 0, 1, and those are just numbers because it reveals the dependence among those. So the goal of reduction is to get a matrix in echelon form, right? An echelon form means that the first non-zero entry in each row is a 1. So we have a 1 leading that row, a 1 leading that row, a 1 leading that row, a 1 leading that row. Each leading 1 is a column to the right of the leading ones in the rows above it. So this one here is to the right of that one. This one here is to the right of these. All rows of zeros are at the bottom. So there's a row of 0. This right-hand side, we're just sort of ignoring for the moment. Right, we're just looking at the matrix of coefficients. And if a column contains a leading 1, then everything else in the row is 0. In the column is 0. So that's the form we want to get things in row reduction. And that, like this thing here, gives us relationships between the vectors. So what's the procedure for this? If you're given a matrix, right, and it's full of numbers, dot, 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 just lots of numbers everywhere, what you want to do is pick out the one in the upper left, and you use that to clear out the numbers below so that you end up with a number here, and then a bunch of zeros beneath it. Right, and that's what we did here. Right, we got that 2 there, we got to clear it out, we got a 0. What's the next thing we do? Well, we want to use this number to clear out things in the column and make them 0. So now we've got a number and a bunch of zeros here. And we take this number here, whatever that is, and use that to clear out whatever's here, 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 and here. So we have a number and a pile of zeros in the first column, and then we get a 0 here and a number here, a 0 there. And you just keep going until you just have numbers in each of the columns. And at the very end, you divide through, because we don't like fractions, to get it to be in reduced form like that. So are these vectors linearly independent? How do you tell? Well, you do k1 v1 plus k2 v2 plus k3 v3 equals 0. The only way that you can have a solution to this is all 3 equal to 0. So how do we check that? Well, again, you turn this into a matrix, but what we saw above is that the coefficients will be this. And we don't need the right-hand side, because the right-hand side is 0 and nothing's going to happen to it. So what we want to do is we want to clear out, we want to take this 2 and clear out this column. So what we'll do is we'll take row 1 and we'll multiply it by 3. We'll take row 2 and we'll multiply it by 6. And we'll take row 3 and we'll multiply that by 2. And what does that give me? 6 minus 15, 3 times 19 is 57. Minus 6, minus 12, 24. And then 6, 12, minus 20. And now we will take row 2 and replace it with row 1 plus row 2. And we'll take row 3 and replace it with row 3 minus row 1. So row 1 plus row 1 is staying the same. We're not tinkering with it in this step. Row 2 is 6 plus minus 6 is 0. Minus 15 plus minus 12 is minus 27. 57 and 24 is 81. 6 minus 6 is 0. 12 minus 15 is 27. Minus 24 minus 57 is minus 81. 27. There we go. Great. So we want to take this minus 27 and clear out everything here. 27, 15 is a little bit tricky to figure out what that common denominator is. So I'm going to simplify things by dividing. What we'll do is we'll take row 1 and we'll divide it by 3. And we'll take row 2 and we'll divide it by minus 1 over 27. And we'll take row 3 and we'll divide that by 27. So what's our new matrix? We go back to the original row 1. And then we get 0, minus 1, no, plus 1, because we're dividing by minus 27. 3, 0, minus 1. So some of this we can do in our head if we want. We can say R1, we want to use this plus 1 to clear out this minus 1 and this minus 5. So we'll take R1 and we'll add to it 5 times R2. And we'll take R3 and we will make a new R3 equal to R3 plus R2. So 2 plus 0 is 2, minus 5 plus 5 times 1 is 0. 19 plus 5 times 3 is 34. Oh, but that should be a minus 3 because I divided by minus 27. So it's not going to be a 34. Right? So this should be a minus 3 here. And then we get 19 minus 15, which is actually 4. And then when we do row 3, actually row 3 just disappears entirely. And then we can divide the top one by 3. So remember that these were the coefficients of K1. These are the coefficients of K2, and the third column is the coefficients of K3. To turn this back into equations, remember that our right-hand side had been 0 all along. This becomes K1 plus 2, K3 equals 0, K2 minus 3, K3 equals 0, because this first column is the coefficients of K1, coefficients of K2, coefficients of K3. So what this procedure does is it takes our method of reduction and it just systematizes it. So you just play with the coefficients until you get what you want. So here, these are linearly dependent. Any choice of K3 gives a solution. So in particular, there are non-zero solutions to this equation, right? And to be linearly independent, there have to be only zero equations. And the second is if we look at we'll call this U1, U2, U3 is those vectors. What we're getting is that 2U1 minus 3U2 equals U3. And so if we go back up to our vectors here, that would correspond to 2V1 minus 3V2 equals V3. Right? And so V3 is actually in the span of V1 and V2. It's a linear combination of those. And so it's linearly dependent. So that's the second thing. Let's put a little 2 around that. That the columns in the row reduced echelon form tells us the relationship among the vectors. And I think okay, so is this in the span of the vectors from example 6? Right, and so this would be slightly different question. Linear independence was saying that the only solution to these three things equal to 0 is 0, 0, 0. But here, what we want to know is there any solution, one or infinitely many solutions to this? And we'd expect there to be infinitely many solutions because we have a duplication in our vector list. V3 is actually a combination of V1 and V2. So again, now this becomes a matrix where we put our three vectors v1 and v2 in a matrix. Minus T6 is v2, 19, 4, minus 12. And we say, okay, so this is 1 minus 5, 15. You follow the above procedure, or better yet, you go to a online row-reduced echelon form calculator, and you say, what's the row-reduced echelon form in this? And it says it's 1, 0, 0, 0, 1, 0, 2, minus 3, 0. That's the same thing that we generated up here for the coefficients, because each column only affects itself. And then we get 3, 1, 0. So how do we read this? This means that K1 plus 2K3 equals 3. K2 minus 3K3 equals 1, and 0 equals 0. Those are my three equations, right? Because this is the coefficients of K1, K2, K3, and this is the coefficients of the coordinates of B. So what does it tell me? Well, any K3 that I choose will give me a K1 and a K2, so there's infinitely many solutions. So the answer is yes. I can write B as a linear combination of these in infinitely many ways. What's a vector that's not in the span? So we want to see, is there a vector that's not a linear combination of these three? And geometrically, we think that there are, because these are three vectors in a three-dimensional space, but only two of them really count. The third one is sort of in that. And so the span should actually be a two-dimensional thing. And so if we take the vector 1, 1, 1, and we do the reduced Fourier echelon form of that, what do we get? We get 1, 0, 0, the usual thing for the coefficients. And now when we actually finish it all out, we get 0, 0, 1 on the right side. So that means our equations become K1 plus 2K3 equals 0, K2 minus 3K3 equals 0, and 0 equals 1. There's no choice of K1, K2, and K3 that'll make 0 equals 1, so there's no solution. So this vector is not in the span of those vectors. So if we want to draw that geometrically, it looks like this. The black vectors are v1, v2, and v3. This vector is, that blue vector is this one, 1 minus 5, 15. And the red vector down there is 1, 1, 1. So the three black vectors, right, they all lie in this same plane. And this vector, the blue vector, lies in that same plane. The red vector sort of sticks out from it. If you take this picture in GeoGebra, you have to use a 3D calculator, and you turn it sideways, you get this. Here's one of our vectors. Here's another vector. This is the plane that they lie on. This is the big vector, 1 minus 5, 15. So that lies on the same plane. And then this is my red vector, 1, 1, 1. That's not in the span because it points off of the plane. So we've been looking at row reduction in terms of vectors, but can also use solve systems of equations, because these collections of vectors, these linear combinations of vectors, are just equations. So we can convert this into a system of equations. We have four equations. Equation 1 is represented by the first row, equation 3, equation 4. And then these are the coefficients of your first variable, coefficients of second variable, coefficients of third variable, and then this is the right-hand side. So our first equation is x1 plus 0, x2, so we don't write that, plus x3 equals minus 4. 0, x1, don't write that. 2x2, 1 there, minus 2x3 equals 10. And then we have a 3x1 plus 2x2 plus 4x3 equals minus 2. And then finally, x1 plus x2 equals 1. And you can go back and forth, right? So an augmented matrix is a system of equations. System of equations is an augmented matrix. And then we can see that the system of equation has, say, 1, 0, 3, 1, this particular vector as its coefficients of x1. So you can look at this and say, is this vector here in the span of these three vectors? That's what this is trying to establish. Or you might have this system of equations from something else. So how do we solve this system of equations? So we do reduction, you eliminate all the variables. What that does is you end up with this. And so if I call this column, so the system of equations you get is this is the coefficients of x1, x2, x3, and this is the right-hand side. So we get x1 equals minus 4, x2 equals 5, x3 equals 0, and 0 equals 0. Important to check that, because if that's false, then there's no solution. So that's true. And so what does this mean? Well, this is your solution to the equation. And you could say that it's minus 4 times this vector plus 5 times this vector plus 0 times this vector is equal to that vector. So the reduced row echelon form quickly gets you the result. Generally, in doing the homework or something, use a calculator online to get the row reduced echelon form. We're not particularly interested in how well you can do arithmetic. So yeah, these three vectors here are linearly independent, right? Because we got this nice row reduced echelon form, 1, 0, 0, 0, 1, 0, 0, 0, 1. So these are linearly independent. There's no relationship between them. And the vector on the right-hand side is in the span of those three. Coincidentally, we didn't need to use x3, but that's just how those numbers worked out. Oh, did I screw up no, example 14. Solve the system of equations using row reduction, use vectors and parameters to solve it. So as an augmented matrix, you get 1, 0, 3. Note that there's no x1 coefficient here. And so we have a 0 for that in the second row. There's no x2 here, right? So we need to have a 0 there for my x2s, a 2 and a 2. My x3s, I've got a 3 and a minus 2 and a 4. And for my x4s, I've got a 1 here and a 3 and a 1. And that becomes 2, 3, minus 1. So as an augmented matrix, that system of equations turns into this, and the row reduced echelon form of that is this. So we have our nice leading ones, right? And we have something for the fourth column, and then there's our answer on the right side. So what is this solutions, right? If this is our system of equations, what are we getting? We're getting x1 minus 4x3 equals minus 8. We get x2 plus 19, that's x4. 19 over 6, x4 equals 29 over 6. And we get x3 plus 5/3, x4 equals 10/3. So we see there's infinitely many solutions because no matter what we choose for x4, we get a value for x1, x2, and x3. So we can rewrite this as x1 equals minus 8 plus 4x4, x2 equals 29 over 6 minus 19 over 6, x4, x3 equals 10 over 3 minus 5/3 x4. So the x4 is a parameter, right? Whatever you choose for x4, you get an x1 and x2 and x3, so infinitely many solutions. You can see that the fourth vector, this vector, is a linear combination of the first three. It's minus 4 times this, plus 19 over 6 times the second column, plus 5/3 times the third column. In terms of vectors, we want something of the form x1, x2, x3, x4 equals something. But we don't have an x4 equal to something here. So we introduce a parameter x4 equal to t. So what does that make our equations now? Minus 8 plus 4t, 29 over 6 minus 19 over 6 times t, 10 over 3 minus 5 over 3 times t, and x4 is t. So I can break this into two vectors. I'll take all the constants out. So the 8, the 29, and the 6, this remember is 0 plus t, so we'll take that out. And then we'll add on the terms involving the t's. And then finally, we can pull the t's out. We have 29 over 6, 10 over 3, 0, plus t, there's our parameter. And we recognize this as a line in 4 dimensions, right? So our solutions to this set of equations can be thought of as a line in 4 dimensions. This is your offset vector here, plus t times your direction vector. And so we can introduce parameters here to represent infinitely many solutions, so we can think about them geometrically a little bit. So having the ideas of span and linear independence leads us to the idea of a basis. The dimension of vector space is the correct number of vectors needed to cover the entire vector space without any vectors. So if V is a vector space and V1 through Vn is a set of vectors that are linearly independent, that's one condition, linearly independent. And the other condition is the span is the entire vector space, then it's called a basis. So the number of vectors in a basis is called the dimension of the vector space, and these are for finite dimensional vector spaces. What's a basis for an infinite dimensional vector space can be a little bit complicated. Some of these you are familiar with, I and j. I is 1, 0, and j is 0, 1. These are linearly independent. Because if we set that equation up, what equations does that become? K1 equals 0, K2 equals 0. Right, so those are linearly independent. Linearly independent means in 2 dimensions that they're pointing in different directions. A basis, does it span if we let V be equal to any vector, V1, V2, in the plane? Then is there a solution to this K1I plus K2J equal to V1, V2? And this left-hand side becomes the equation K1 times 1 plus K2 times 0 K1 times 0 plus K2 times 0, K2 times 1. So the V1 and the V2, that's the K1 and the K2 that you need to get the vector V1, V2. So any vector V can be represented as a linear combination of those two vectors. And that should not be V1 there, it should just be V1I. So that's a basis. Same way, IJK in 3 dimensions is a basis. The argument is the same, so I'm not going to reproduce it. Depending on how you like drawing your axes, I like X, Y, and Z here. I in 3 dimensions is that vector. J in 3 dimensions points along the y-axis, and K in 3 dimensions points along the z-axis. These are called the standard bases, IJK 100, 010, 001. And the standard basis in n dimensions is the same thing with n entries, and you just have one of them one being a 1. So, can other things be a basis? Sure, V1 equals 1, 1, and V2 equals minus 1, 1. Geometrically, this isn't actually that hard to look at, right? V1 is this, 1 unit in the x direction, 1 unit in the y direction. V2 is minus 1 unit in the x direction, and then 1 unit in the y direction. So that's V2. They point in different directions, and so in 2 dimensions, you can say, well, they're linearly independent. So show that these are a basis. Well, show that they're linearly independent. We've done this several times. We need linearly independence is that K1 and K2 have to be equal to 0 for this equation to be true. So K1 minus K2 equals 0. K1 plus K2 equals 0. If you add these together, we get 2K1 equals to 0. So K1 equals 0, K2 equals 0. So that's not too hard. We don't even need to use the reduction there. So they're linearly independent. Do they span? So span is answering this question. It's almost the same question because we get the same things on the left side, we get different things on the right side, but we can still solve this. If you're given W1 and W2, what do K1 and K2 have to be? Well, add the two things. 2K1 equals W1 plus W2. So that tells you what K1 is. And once you know what K1 is, you can solve for K2. And you actually get K1 equals wait a minute. K1 equals 1/2 W1 plus W2. And then K2 is 1/2 W2 minus W1. So no matter what W1 and W2 is, you get a K1 and K2. So any vector is, in fact, in the span. So 7 minus 3. That means that K1 should be 1/2 W1 plus W2. So it should be 1/2 of 4. And K2 should be 1/2 of W2 minus W1 minus 3 minus 7 is minus 10. It's minus 5. So if we go, V1 is like this. If we go 2V1, and then we go minus 5 V2, V2 is like that. So minus 5 of that would be kind of long. We add those two vectors together. We get our vector W, which is 7 minus 3. So that's a basis. A basis can be just any two. In R2, it's any two linearly independent vectors. In R3, it's any three linearly independent vectors. So here, can two vectors be a basis for R3? The answer is no. You need at least three, right? Because two vectors will give you a plane, but that's not all of R3. Can four vectors be a basis for R3? The answer is no. There's too many, right? In 3 dimensions, you can only pick out 3 different directions to go in. So the fourth vector is sort of an extra vector, right? It'll be in the span of the other 3. Is every set of 3 vectors a basis for R3? Three vectors might not be linearly independent. So we come back up here, right? These 3 vectors in R3 were linearly independent. This fourth one is not. It's a linear combination of the other 3. So that was 4 vectors. I was pretty sure I had 3 vectors up here somewhere. Well, we'll go fishing for it now. But yeah, if they're linearly dependent, if one is in the span of the other ones, then it's not a basis. So if we go back to differential equations, are these a basis for the solution of this differential equation? Well, this is r squared minus r minus 6 equals 0 is our characteristic equation. And that consists of 2 vectors. And so we said that the general solution is k1 e to the 3t plus k2 e to the minus 2t. And so is that a basis? Well, is it linearly independent? K1 e to the 3t plus K2 e to the minus 2t equal to 0 forces K1 equal to 0, K2 equal to 0. And the answer is yes, right? If we take this equation and multiply through by e to the 2t, we get K1 e to the 5t plus K2 equals 0, or K1 e to the 5t equals minus K2. And so since t is a variable, this side changes, but K2 is a constant, that one doesn't. So the only way that this can work is if K1 and K2 are both equal to 0. So they're linearly independent. Do they span? They do. All solutions are of this form, right? And so we're talking about span. In this case, we're saying, okay, well, span means that all the solutions, if this spans the solutions of the differential equation, then all solutions must be of this form. And it's true, but we don't know exactly why yet. We've said that, but we haven't actually drilled into why that's actually true. And it's connected to the fact that this is a second derivative, right? So you get 2 constants, a K1 and a K2. But we want to formalize that a little bit, and we'll see that coming up. Same thing about this. Are these a basis for the solutions of that differential equation? And our characteristic equation would be r cubed minus 2r squared minus 5r plus 6 equals 0. It's a cubic. It's hard to factor, but fortunately, I'm not going to actually do that. And we'll just say that our solution should be e to the t, e to the minus 2t, e to the 3t. And so we expect the general solution to be that. So is these three vectors, e to the t, e to the minus 2t, and e to the 3t, are they linearly independent? So none of them can be written in terms of the other two. And do they span? Are all solutions of this form linearly independent? Means that we want to know if this equation equals 0, has only solutions k1 equals 0, k2 equals 0, k3 equals 0, has solutions. Well, it does, but it's a little bit harder to show because we need this to be true no matter what t is. So no matter what number I plug in for t, I want this to be equal to true, to be equal to 0, and that the only way that can be is k1, k2, k3 equals to 0. So how can we actually solve this? Well, if it's true for all t, we just pick some convenient values of t. So suppose we take t equal to -1. That gives me k1 times e to the -1 plus k2 e to the -2 plus 2 plus k3 e to the -3 equals 0. Take t equal to 0, that gives you k1 plus k2 plus k3 equals 0. And take t equal to 1. So since this has to be true for all equations, all values of t, it must be, in particular, true for these three things. So we get this system of equations. What do we do with the system of equations? We turn it into a augmented matrix. And you say, well, what are the only solutions to this? Well, you go to reduce from echelon form, and your calculator says that the only solution to this reduced from echelon form is this. And so our solutions are that. So we can show they're linearly independent. The question is do they span? Is every solution of this form? And the answer is yes, it is, but we need to be able to do a little bit more to be able to answer that. So are there bases for function spaces? Kind of. Depends on the function space. There's a class of functions called analytic functions, right? And a Taylor series gives you a basis, right? Because if f of x is a analytic function, that means that you can rewrite it as plus f prime at 0 times x plus 1 over 2 factorial f double prime of 0 times x squared plus 1 over 3 factorial third derivative at 0 x cubed plus dot dot dot. So number, take the vector here to be 1, f prime of 0 is a number, x, we'll take that to be a vector, 1/2 f double prime of 0 is 0, x squared is a vector, x cubed is a vector, this is a number. So f of x then is a linear combination of the functions 1x, x squared, x cubed, dot, 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 dot. And so that gives us a basis for a particular class of functions. Fourier series is another one. we can write functions as being a constant plus a constant times sine of x plus another constant times sine of 2x plus dot 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 plus a constant times cosine of x plus another constant times cosine of 2x plus dot dot dot. And there's some restrictions on what kind of functions can be expressed like this. And that gives us a basis of 1. And then we take sine x, sine 2x, cosine 2x, sine 3x, cosine x, cosine 2x as being our basis for those things. Okay, so that's the end of that.